Starship V3, the most powerful rocket ever built, just made orbital AI data centers economically viable for the first time in history. Everything the tech industry believed about where AI computing had to live buried in ground-based server farms burning through land, water, and power grids was built on one assumption: that reaching orbit cost too much. Starship V3 just broke that assumption. And the implications for AI, for energy, for who controls the future of computing are only beginning. In the next 12 minutes, you will find out exactly why Starship V3 changes the math on orbital computing, who is already quietly building for this moment, and what it means for the $500 billion AI infrastructure race happening right now. Starship V3 can carry 300 metric tons to low Earth orbit, nearly 3 times what any rocket has ever managed. And the part almost nobody is talking about: the energy economics of orbital solar are now better than building a new data center on the ground. But the question nobody has asked out loud until now is this: if orbital AI infrastructure becomes real, who controls it and who gets locked out? That is what this video is about. Here is the problem hiding inside the AI boom. Every major AI model running today, GPT, Gemini, Claude, Grok, requires enormous continuous computing power. And that power has to live somewhere physical. Right now, it lives in data centers, enormous buildings, often the size of several city blocks, stuffed with tens of thousands of GPU chips designed by Jensen Huang and his team at NVIDIA, chips that generate extraordinary amounts of heat. To cool them, data centers consume millions of gallons of water per day. Microsoft, Amazon, Google, all racing to build more. Andy Jassy, CEO of Amazon, has committed over $100 billion to new data center construction through 2028. Satya Nadella at Microsoft has pledged another $80 billion. The land use is staggering. The power demands are cracking regional electrical grids. There are now cities in the American Southwest where water authorities are refusing new data center permits entirely. There are states where power companies are warning they cannot add another gigawatt of demand without years of new grid construction. The AI industry is running into a physical ceiling, and the ceiling is getting lower every year. Now, here is where Starship V3 changes everything. What if you didn't need the ground at all? If this is the kind of deep dive you want, subscribe before we go further. Now let's talk about what happens when you move AI into orbit. The physics of orbital computing are almost counterintuitive. In low Earth orbit, there is no weather. There is no cooling problem. You radiate heat directly into the vacuum of space. There are no water permits, no land restrictions, no neighborhood opposition to a server farm in your backyard. And most critically, the sun never sets on your solar panels. In geostationary orbit, solar panels receive energy 24 hours a day. On the ground, even the best solar farm captures energy for perhaps 6 hours at peak efficiency. Orbital solar panels receive roughly 8 times more energy per unit area than their ground-based equivalents. This is not a new idea. Scientists have been proposing orbital solar power since the 1960s. The physicist Peter Glaser first published the concept in 1968 in the journal Science. NASA commissioned serious engineering studies on it in the 1970s. The European Space Agency has had active orbital solar programs running for years. The reason it never happened? Launch costs. Getting 1 kilogram into orbit has historically cost between $5,000 and $20,000. At that price, you could never make orbital infrastructure economically competitive with a data center you build in Nevada. Starship V3 rewrites that equation. SpaceX's internal projections and the estimates that lit up Reddit's r/accelerate suggest that with full reusability, Starship V3 could drive launch costs below $100 per kilogram within 5 years. That is a 50 to 100 times cost reduction compared to where we started. At $100 per kilogram, the math on orbital AI infrastructure stops looking like science fiction. It starts looking like a capital allocation decision, and this is where the corporate chess game gets interesting. Microsoft, Amazon Web Services, and Google Cloud are all already operating satellite computing programs, but they are small, experimental, the kind of thing you fund quietly while you wait for someone to crack the launch cost problem. Elon Musk cracking it changes everything for them, and Musk knows it. Starlink SpaceX's satellite internet constellation is already the largest orbital infrastructure project in history. Gwynne Shotwell, SpaceX's president, has said publicly that Starlink is the foundation, not the ceiling. Meanwhile, Sam Altman, CEO of OpenAI, spent much of 2024 and 2025 pursuing a different approach to infinite AI power: dedicated nuclear plants to feed AI data centers. Altman was betting on the ground. But here is the quiet irony. Altman is also an investor in companies working on satellite computing. He has not bet exclusively on either side. He is watching the orbital economics the same way everyone in the industry is watching them very, very carefully. Now let's talk about the technical leap Starship V3 actually represents, because this is not just a bigger rocket. The fundamental architecture changed. Starship V1 and V2 used Raptor 2 engines. V3 introduces upgraded Raptor 3 engines, simplified manufacturing, and a dramatically increased propellant load. The Super Heavy booster in V3 produces roughly 263 metric tons of thrust from 33 engines. The ship upper stage is redesigned for greater propellant efficiency. The result, 300 metric tons to low Earth orbit. For context, the Saturn V, the rocket that sent humans to the moon, could carry 130 metric tons. Starship V3 more than doubles that. But the real innovation is not the payload number, it is the reusability target. SpaceX is targeting turnarounds of less than 1 hour on the booster, not days, not weeks, 1 hour. If that becomes routine, the economics of access to space change permanently. Here is the counterintuitive truth that analysts are only now beginning to model. The most expensive place to build an AI data center might soon be Earth. Because when you factor in land acquisition, water rights, power infrastructure, cooling systems, and permitting timelines averaging 3 to 5 years in developed countries, and compare that to an orbital facility powered by unlimited solar, with no cooling problem and no regulatory bottleneck, the ground stops looking cheap. It starts looking like the legacy option. And this is the part that transforms the story from a technology story into a geopolitical one. China is not watching from the sidelines. China's space program under the China National Space Administration and private players like Landspace has been explicitly developing heavy lift capability toward the same orbital payload class. China's government has invested billions into an orbital solar power demonstration program. The Chongqing University team has been building and testing components since 2020. China's stated goal, a demonstration orbital solar plant by 2030 and full-scale operation by 2050. If orbital AI infrastructure becomes the dominant compute model of the 2030s, the nation that controls the orbital layer controls where AI runs, and AI by that point will be running almost everything. If that changed how you see Starship V3, subscribe now. This is not just a rocket story, and what comes next will completely change how you think about who controls AI and who doesn't. So, here is the answer to the question we opened with. Who controls orbital AI infrastructure and who gets locked out? The window is narrow, and it is measured in years, not decades. Right now, in 2026, Starship V3 is making its first flights. The launch cost curve is not yet broken, it is bending. The companies and governments that move in the next 3 to 5 years to establish orbital compute presence will be the ones who define where AI lives for the next 30. This is not abstract. The Starlink constellation is already occupying specific orbital bands. Orbital real estate, the specific altitudes and inclinations where satellites operate most efficiently, is a finite resource governed by the International Telecommunication Union. First movers will file for those slots, late movers will find them taken. The United States has an advantage right now. SpaceX. Starship V3 is, for the moment, in a class by itself. No other nation or company has a vehicle in this payload class with this reusability ambition on this timeline, but advantages are not permanent. The European Space Agency has signed a €40 million contract with Avio to develop a reusable upper stage demonstrator. Europe is watching. India's ISRO has stated heavy lift ambitions. The race is not over, it is just beginning. Here is what is different about this space race versus the Apollo era. The Apollo race was about prestige, flags, and footprints. What a nation could demonstrate. This race is about infrastructure, about where computation, the substrate of modern civilization, physically exists, about who writes the rules for AI systems that will make medical decisions, financial decisions, military decisions. The company or government that establishes dominant orbital AI infrastructure in the 2030s will occupy the same structural position that whoever built the internet backbone occupied in the 1990s. That is not a metaphor, it is the same logic applied one layer up. And Starship V3 is the first rocket powerful enough and potentially cheap enough to make that infrastructure buildable. The race to own orbital AI infrastructure is the new space race, and unlike Apollo, the winner will not plant a flag. They will control where the world's intelligence runs. Starship V3 is not just a rocket, it is the key that opens a door that was previously locked. What happens next, and who walks through that door first, may be the most consequential technology question of the next decade. Subscribe if you want to keep watching this story unfold.